so much. Yes, first the way this talk came about is that I was attending this workshop last week in O1 physics and quantum information and quantum field theory and quantum gravity, and so Avi learned about my other life and he recruited me to talk about tensor networks. So I'm happy to oblige. So I guess I just want to since this is sort of the computer science discrete mathematics seminar, as I understand, I want to sort of try to explain things from this perspective. So for those of you sort of for the physics or mathematical physics background, it may be a bit boring, or if not boring, a bit strange. But you know, I hope you'll bear with me. And anyways, please feel free to interrupt, and we can make this more of a discussion than sort of a lecture. So I want to talk about this thing called tensor networks. Is this readable?
Yeah, very.
Okay, excellent. And so the goal of tensor networks is to find succinct descriptions of high-dimensional tensors in high-dimensional space of tensors that are sort of rich enough to capture tensors of interest and hopefully also amenable to sort of efficient computation, in the sense that we can extract. We can not only efficiently store these objects, but also extract expectation values and other quantities of interest. So that's sort of the goal, and so that's we try to write this down. Descriptions of tensors, and a tensor for me will be alternatively an array of numbers or something in this space. So I'll always use D for the local dimensions and N for the total number of systems. And so the prime reason historically why we care about tensor networks is that, or why we care about describing tensors, that tensors arise naturally as describing states of quantum systems with many particles, and would typically correspond to a number of particles. And so these, you know, in sort of a material of sort of a not too small size, N is really large, and so we can't hope to represent this tensor by just listing its coefficients, and so we're trying to look for other representations. So that was sort of the goal. So we would like to do this to represent or describe, for example, quantum states of many body systems. Among other things, but you could also say, okay, maybe we just want to represent a function, you know, that has sort of n inputs, you know, the ith input ranging between 1 and di, and it assigns a number to it. So that's a function on with many possible inputs, and we want to characterize this in some way. And so there's multiple ways by which one could go about characterizing such an object. So maybe I'll put this here. So these are sort of attempts that we'll not pursue. So one way would be to just have a classical circuit, and I sort of tell you the index, I1, I2, up to IN, and the output will be the amplitude, the component of the tensor. Okay, so that would be one way of going about it. So here are some attempts. So, sorry. So in come some indices, I1 to IN. So these are just discrete between, I1 is between 1 and D1, up to IN between 1 and Dn. So these are inputs to some black box. Maybe this could be a circuit or some program, some algorithm, and the output will be some component of this tensor. Okay. So this is a perfectly fine way by which one could represent a tensor. So this wire, right, I said was discrete. This wire would be, say, a scalar, so say a complex number. But it's not a very useful representation for all kinds of questions that we may, for some of the questions that we may care about. For example, suppose we want to compute something like the norm squared of the tensor, then it seems we have to probe this black box over all possible inputs. So for this kind of question, it's not clear whether that this is a good representation. Okay. So another thing that we may want to do, so maybe but sort of estimating or computing this seems to be tricky. Another thing that we could do is we could try to maybe produce a box that samples. So imagine we have a tensor. Let's say the L2 norm is normalized to 1. Then the component squared form a probability distribution. And we could ask for a box that sort of samples from such strings I1 to IN according to this amplitude squared, to these probabilities. Okay, so that is something that one can do. So maybe let's say classical, maybe probabilistic circuit for sampling. Didn't work out just as well as I like to. Sorry. This is hard. Okay, so here I'm thinking we just have a box, and it outputs I1 to IN according to the probability distribution, which is given by Ti1 IN squared over, say, the L2 norm of T. So if I write norm, it will always be the L2 norm squared. So that's something one could do, and for example, one could it's sort of fashionable to use, for example, a neural network, some generative neural network to this, a hidden Boltzmann machine or something like this. And so that's one way by which one could represent amplitudes of a quantum state, and people have done this. That will not be the approach that we pursue, but it's useful for some problems. So what we want to do is we want to consider circuits where the or formulas where the wires correspond to actual vector spaces rather than to single scalars. We're having multiple wires in parallel means a tensor product of vector spaces. Okay, so I want to define what I mean, sort of first pictorially, and then maybe we can give a precise, rigorous definition if you like. So today, so these are not things that we're going to pursue, but instead we want to pursue tensor networks. And the idea behind a tensor network is basically that we start with low-dimensional tensors, in particular tensors that have few indices. And then we are trying to build a big tensor by taking many of these small ones and contracting. So that will be sort of the approach. And depending, of course, what structure, what sort of graph, what network you choose, you get a different family. And so you get different families of quantum space, of quantum states or of tensors that form some low-dimensional subspace of this big tensor product. And hopefully they characterize an interesting subspace or interesting subset, submanifold of this vector space. Okay. So here, so the pictorially this goes as follows. So suppose we're going to use pictures that look like this. Whenever I have such a bubble or a box, this will correspond to a tensor. The tensor has as many tensor factors or indices as there are legs coming out of the bubble. So for example, this thing would correspond to a tensor with components T, A, B, C. And then there's some dimensions, dA, dB, and dC. Maybe I'll label those for clarity. This is the A, this is the B, and this is the C leg. So that's going to be the notation. So far, so good. Okay. So the only additional rule that we need is when we have two of these things and we hook them up, and that's going to mean contraction. Yeah, my talk will be totally on the level of pictures, and there will be some theorems interspersed, but will be mainly pictures. So here is another picture. So suppose we take one of these tensors and another one. So maybe this is A, B, E, C, D, E. Another E, maybe E prime. Now suppose we hook those up. This will correspond by definition of this calculus, of this graphical calculus, to a contraction. And so this will correspond to a tensor. Maybe we'll suppose if this is a tensor called T, that's another tensor called S. Then this whole thing will correspond to now a tensor with 1, 2, 3, 4 indices. Maybe we'll call this U. And we'll call these, say, A, B, C, D. And the components will be just given by the contraction. That is the sum over all possible values for E, T, A, B, E, S, E, C, D, or maybe C, D, E would be more natural to write. We always know which leg corresponds to which index because we have these nice labels. Okay, so that's going to be in a tensor, right? And C, D, A up to C, D, D. So now we can build up, tensors with more and more indices in this fashion. And as long as each of these, as long as we don't have too many of these tensors, say if you only have polynomial domain in some scaling parameter, and each of these things don't have too many legs, this will be an efficient way, an efficient description of some tensor in this high-dimensional space. Okay. It's also going to be useful maybe that we give meaning to just a single line. So if you just have a single line, this will correspond to, I guess, a tensor with two indices, which is just the identity map in a way. So this we can think of I guess the identity map with the unit tensor, or say the tensor with indices delta AB. Okay. And so I draw these pictures, but of course one can make them rigorous. So one can use, for example, formalism of tensor categories to assign sort of unambiguous meanings to these pictures. I'll be a bit sloppy, but please do interrupt me if something doesn't seem kosher. Okay. So the point is that we have these pictures. So this is a simple example of a tensor network. And any such picture defines a tensor. Sometimes these tensors are also called tensor network states because we think of quantum states. So tensor network I'll abbreviate by Tn, and this I will abbreviate by Tns. Okay. So that's the approach. So maybe we can practice with representing some small tensors that we like. So let's look at some examples. So for example, suppose that we start with a tensor. I'll omit the names if they're not important, which is just a unit tensor. So EI, tensor EI, tensor EI, I going from 1 to D. So that's a 3 tensor. People call it a unit tensor. Then you could ask, okay, what does this thing correspond to? Anyone? Okay, so that is, of course, a unit tensor that has now 1 to up to n indices. Okay, because by the way this contraction works, we're going to match EI from here with EI from there. So this object is going to represent EI tensor n. So we can build, large unit tensors from small ones. So that's one particular example. Maybe we'll look at another simple example. So maybe this is sort of a pretty homogeneous state. Maybe we can look at another one where somehow something that's known as the W tensor in the literature. So here we take as sort of our little tensor the following object. So this is ABC. So I want to define the ABC component of this tensor to be either 1 or 0, and I want to define it to be 1 if ABC is either say these dimensions are two-dimensional each. So that's going to be a tensor in C2 tensor C2 tensor C2. And I want to set this thing to 1 for the following combinations. Either if all of the indices are 1, if we have something like 2, 1, 2. Actually, maybe let me do it differently. 0, 0, 0, 1, 0, 1, and then I want to do 0, 1, 1. Okay, so there's 3 non-zero entries in this tensor. And then, if I didn't make a mistake yesterday night, I can look at a larger tensor network where I use this as a building block. So I'll take many of these. And then at the end, I'll insert certain vectors. So I'll start with the, say, 0 basis vector here, which is a tensor with a single index. And I'll end with the E1 tensor over here. So now if I look at what's going on, right, sort of, so each of these indices, this will now be a sum of, certain basis states, product basis states. But sort of in those two cases, this index will be 0, and we'll sort of, we'll just copy. So if this guy is 0, we'll copy 0 over here. So that will be this case, and we'll emit 0 here. We can also use this tensor entry, right, which will emit a 1 here, and at this point, this index will be 1. But then somehow we are left with this option, right, and we have to root 1 through, and we'll get zeros all the way. So this is a tensor that looks in the end as follows. It's basically E100 plus E010. So it's a superposition of all these product basis states So I'm omitting the tensor products, where one index is 1 and all the other ones are 0. Okay, this is something that sometimes pops up. Sometimes it's called the W state. Okay, so this was some toy examples. Maybe we can look at a more interesting one. Good. So here's another one. So suppose we have the following network. Let's say tensor A, a tensor A, a tensor B, and a tensor C. So A, B, and C are 2 tensors each. So we can think of them as matrices if we like. So then what is this object? That's exactly the matrix multiplication tensor if you think of A, B, and C as variables, right? Because I mean, so this thing is supposed to be a number. There's no dangling legs, and we are contracting, right? Say if this is Aij, then maybe you call this I, J, and K, and this is exactly well, actually it doesn't. Maybe I won't write it down. That's exactly trace A, B, C. If you think of A, B, and C, if you order the indices of A, B, and C in the right way, okay. So that's interesting. So in particular, we can sort of think of A, B, and C as variables, so we can remove them from the network. And so we basically just have a picture with 3 edges like this. And we think of this. These as dangling edges, these as dangling edges, and these as dangling edges. So that's now a tensor that lives in CD squared, tensor CD squared to the CD squared. And that is the matrix multiplication tensor. Right? This was a particular trace. If I fill in the values, if I don't fill them in, then I get the matrix multiplication tensor. Okay. And so one can, okay, so explicitly, right, yeah, maybe that's okay. And depending on what these dimensions are, we have rectangular matrices that we are multiplying. So that's that. We can also do, maybe we'll call this MM, matrix multiplication tensor, for certain dimensions D1, D2, D3. This is D1, this is D2, this is D3. Now we could also apply some linear map here, sort of from D squared to D squared, maybe alpha, beta, and gamma. Right, this will correspond to applying some triple of matrices in the right way to this matrix multiplication tensor. So in particular, if alpha, beta, and gamma are inverted, we could think of this something in the orbit of this matrix multiplication tensor. That's, I guess, an object of interest to some people here. Okay, and we can use this graphical calculus also to verify certain rules. For example, it's clear that if I look at something like a 4 cycle, this will correspond to an iterated multiplication matrix multiplication tensor. And I guess it is true that if you take a matrix multiplication tensor of 3 matrices and another one, and we glue them together, right? We get this object. So you can play these rules on the level of pictures, but of course it's clear what's going on. Maybe one last sort of thing on this bestiary of tensors. If you have a tensor and you're interested in its norm, then of course you can just take 2 copies, like so, and maybe you take the complex conjugate here. You just hook this up. This is a picture corresponding to the norm squared of the tensor, right? Okay. Good. So in general, so what's the point? In general, let's just briefly collect what kind of data we need to define one of these tensor network states. So we'll have some graph. And sort of, okay, these pictures, they had dangling edges. The way I want to model is that I will have vertices that correspond to the actual vertices in the graph. And then I will have sort of fake vertices for these terminals. So my vertex set I'll decompose into a set V, and a set I'll call delta, like boundary. Then there will be a set of edges, and this will be just some graph. So that's part of the input. The next thing I need to specify is I need to specify the dimensionality of all of these edges in my graph. So for each edge, I want to have an integer. So these integers I associate to edges. Now I could ask, okay, so suppose I know, this is 2-dimensional, this is 5-dimensional, this is 7-dimensional. I want to know, okay, what's the dimension, or what is the vector space in which the tensor at this vertex has to live? I just, of course, have to multiply them. Or more generally, I can define what is the vector space, hx, corresponding to a vertex. That's going to be just a tensor product of all these edge Hilbert spaces where this edge E is incident to x. Okay, so I hope this this notation makes sense. So with this tilde line, I mean E is an edge that is incident to vertex X. Okay.
This is just notation. That's not input you have to give to the.
Sorry, that is sort of a, yeah, that's right. That's my definition sort of that I'm using for the third part of the input. Thanks. So input is this G, this set of integers, and then indeed it will be one tensor for each of these living in this HX for each X in this inner vertex set. Yeah, that's right. So it will be a collection of tensors. Tx and Hx for all of these guys. Okay, so that's sort of the input done, the thing inside the box. And so this now defines a tensor in, the tensor product of all these Hilbert spaces for X in this boundary set of boundary vertices or terminals or dangling edges. So that's that. Awesome. And then we'll one last bit of abstract nonsense. We'll use this notation, T and S, as in tensor network states for a given graph and collection of bond dimensions. This will be a family of tensors. The family of tensors that can be obtained by varying all these Tx's. That's going to be my notation. Okay. Good. And so so that's the setup, and so the rest. Any question? Yeah.
So this matrix multiplication tensor, is there no significance to these three lines being drawn in a triangle? You could have drawn them however you wanted, like three parallel lines or whatever.
You mean I could have also parallel lines?
Yeah. So I'm just wondering. It seemed like there was some sort of significance to the way it was drawn, but that's not actually part of the input, right?
Like you mean how I lay out this thing in space? No, that's true. But I mean it is important that there's an edge between any pair of these spaces, right? Like for example, if this edge was going here, then this input would be a 3 tensor, and you wouldn't contract things. But sort of comparing this picture with say this one, that's sort of just convention, in some sense.
To draw 3 parallel lines, it would not be clear that it's
3 parallel lines.
Yeah, 3 parallel lines is the same picture. It's not clear that it's a matrix multiplication.
Oh yeah. You mean like
before you say which ones you are.
That's correct. Yeah. So when I had these like little dots around, I meant to indicate what I think of sort of the elementary building blocks. That's right. So so you're totally right. So in a sense, it's just like a tensor product of 3 identities, which is regrouped in the correct way, such that we think of each of them of the right pairs as matrices.
Right. You really
That's
care
right.
about putting the circles there, but you either put the constants for tensors or variables for unknown tensors.
Yep. Yes. So yeah. I maybe another way, of saying is sort of, yeah. No. Does that make sense or?
I think I'm good.
Okay. Yeah. Yeah, so yeah, when we make this identification, indeed, like you have to know if you take these matrices, these variables A, B, C, where do I plug them in which of the 2 legs? That's sort of something that was hidden when I removed these guys. That's correct.
But which is the order? I'm confused about that.
Yeah, so in these pictures, I'm being somewhat sloppy about it, I guess. That's right. Sort of.
I mean, ABC is not the same as CDA.
That's right. So here somehow it would CBA.
I mean, if the dimensions are different, then it's clear. But if the dimensions
Yeah. So I mean, to make this more correct, one should somehow identify the space of matrices with CD tensor CD. I should pick some order, and then sort of maybe add subscripts in the right way. So there's some. So in a sense, it's I mean, in this notation, everything will be fine, right? Because all these vertices, they have distinct identities, and when I would write down this graph and label things correctly, everything would be good. But that's something that's being suppressed sort of by convention in this picture. So I guess here, if I try to make things precise in this notation, say for this tensor, in some sense there would be 1, 2, 3, 4, 5, 6 vertices in this delta. There would be these 3 edges, and then the way I define the connectivity of these vertices as well as the, so this then would define a tensor in a 6th tensor power of CD. But then the way I identify this with the triple of matrices is sort of where indeed, which will determine whether I do, say, trace ABC or trace CBA. That's right. Yes.
So somehow this picture doesn't have any order associated to it, then. But if you want to write it down as a tensor in Cn squared, that's a Cn.
Yeah, that's right. So I mean I think there's several ways of going about it. One would be to be more specific about how sort of the row and the column index of A map to these two lines. Another maybe mathematically more conceptual thing would be to use dual spaces. So if whenever you have an edge, maybe you have an oriented edge, and you think of this as actually an identity map from the dual from one space to the other, or a tensor in V star, tensor V. And then somehow there's only one natural way of associating a matrix with an object in V tensor V star. And so this would be one way of removing ambiguity. In this particular case, where we have one V and one V dual for each input here. In general, though, you probably have to label things in some way to make it distinct. So I agree that somehow there's some convention that needs to be done so that this inequality is literally correct. Yeah, so for example, I don't know, I could do something like this. All right, good. So rest of today, I kind of want to first I want to say some things about what are sort of the general properties of these tensor network states. So how, in a sense, particular ways in which they deviate from being generic, and we'll focus in particular on ranks, simple matrix ranks, not tensor ranks, and entropy. So this will give sort of an indication of what are the limits to these to the expressiveness or the richness of these classes, and what is the significance actually of the graph that we chose, of the underlying graph. So right, for example, here, right, we had this line. This is something that we'll talk about again. It's called a matrix product state, or a finitely correlated state. Here we had the cycle, right? But you could also have some two-dimensional pictures. So what is the meaning of this graph? How does it constrain? Your tensor? So that's what we want to talk about next. And then I want to talk a bit about sort of how do we actually compute with these tensor networks, and what is the computational complexity of certain operations. So is it simple to, for example, compute the norm squared of a tensor network, or is it not? And I mean, you may already know the answer, so then we can be quick. And then finally, I want to talk about, so that's sort of the complexity of evaluation. Then I want to talk about sort of learning a tensor network state, or how do we actually find a tensor network that approximates some tensor of interest. And so first thing we have to talk about is, of course, what is the source, what is the origin of the tensors that we care about. So we'll talk briefly about local Hamiltonians, ground states, and then I can sort of present what is known, and what is known is mostly results in one dimension for one-dimensional quantum systems. And I hope to sketch sort of give a sketch of the state of the art there, and say what, yeah. So that's the plan for the rest of today then. Let's see how this goes. So maybe we'll start with talking about some basic properties. Let's say something simple first. Of course, the number of parameters is very simple, right? Sort of we have to essentially. So what I want to imagine I fix G and at these dimensions, and then I get this manifold of tensor network states, or say the set of tensor network states. So I've fixed G and these dimensions. Sometimes they are called bond dimensions. So if you hear me saying bond dimension, I mean the dimension associated with edges. So that's, of course, we have to provide one tensor for each of these vertices V. And then the dimensionality of this HX Hilbert space, vector space, of course, just this product. So that's the formula we get. So very, very roughly speaking, right, we have something like the number of vertices. Then we have something like the maximum of all these dimensions, these bond dimensions, times the maximal degree of this graph, right? That's sort of a coarse upper bound. So clearly, if the degree is bounded, if this dimension is sort of polynomially large or sort of small in the corresponding context. If there's not too many vertices, then this is a very low-dimensional set, and it can be represented efficiently. And it is also completely not generic in this, big exponentially in n large vector space of all tensors. Okay. So next I want to just show you two interesting families, and they're sort of important both because they're what physicists use all the time, but they're also sort of illustrative for what comes. So the first one are these matrix product states, or finitely correlated states, which go back to Van, Nachtigall, and Werner, MPS. So there's lots of sort of abbreviations and jargon in this business, so please interrupt me if I'm using it without defining it. So here the idea is G is just a linear chain, or maybe a cycle. For simplicity, I'll just look at the linear chain. So it's a one-dimensional chain of some length, say n. And it looks exactly like the pictures that we drew beforehand. And one can look at versions where all the tensors are the same, and maybe you have cyclic boundary conditions. So we look at a cycle, or ones where the tensors are different. Okay. So these are customarily one has some dimension d here, which is fixed by physics. For example, you have some spin 1/2 system, then this d is 2. And this capital D is something you get to choose, and you're trying to minimize it. If it's not too large, then this is an efficient representation. If it's too large, well, you can represent any quantum state, but it's not so interesting. So these guys would correspond, these dangling edges correspond to these vertices in delta. This corresponds to vertices in V, and we get to choose all these tensors. Okay. So here we get some set MPS, parameterized now by the number of sides on these two dimensions. That's a subspace of CD tensor.
All the bottom lines are little d.
These are all, yeah, that's right. These are all little d. So just for simplicity, I'll choose them all to be the same. Yeah. But for now, I'll allow these tensors to be distinct at each side. Okay, and so here, sort of the dimensionality is, of course, n dd cube. And so this is parameterized, right, by n 3 tensors, or if you like, you could also say n little d tuples of capital D by capital D matrices. Okay. By n d tuples, and I'll maybe use some notation like so, where x labels the site, and I labels somehow the index in this d tuple of d by d matrices. And the reason I want to write it like so is because now I can write a particular coefficient. So I can ask, okay, suppose this represents some tensor t, some big tensor t in CD tensor n. I can ask, what are the components of this tensor? So this would be such a component. Now, what is this thing given by? Well, it's basically given by. Okay, I guess I was being slightly sloppy here because sort of for x equals 1 and x equals n, that's not a d by d matrix, but a 1 by d and a d by 1 matrix. So maybe I should say 2 less equal to x less equal to n minus 1, and then for I guess we could say we have two maybe we can say a1 I and an I are sort of, well, 1 by d respectively, d by 1 matrices are just vectors, covectors. So that maybe let's just say these are vectors. So then we can write this as a I1, 1, and now a product I2 up to In minus 1, I2, In. Well, that's too bad. Minus 1, In, n. Sorry, let me make this slightly nicer. Sorry about that. So we have these matrices in the middle. Maybe I'll call this V just because they're vectors. So we have a vector at the beginning, or V1, well, a d tuple of vectors at the beginning, and another d tuple of vectors at the end. Sorry, and these are vectors. Okay, so now we can try again. So for each index here, we get a vector here. This is a v1. We have vn here for each index I, and now this whole component of the tensor is given by starting with this right-hand side vector, which is labeled by in, applying a sequence, multiplying with all these matrices corresponding to our choice of in minus 1, in minus 2, and so on. And then at the end, we choose a vector corresponding to the index I1. and we compute this inner product. Okay. So in the end, sort of what's happening is you have a product of matrices, right? And that's why they are called a matrix product state. Okay. If you had something like these cyclic boundary conditions, then it would just be trace, which is what I was going to write down beforehand.
It is weird with your notation. I mean,
Yeah.
every intermediate node has degree 3.
That's right. So
How come it's a matrix?
So
Notation.
I think my notation is a bit confusing. So x labels these nodes from 1 to n, and then for each x I have a little d tuple of capital D by capital D matrices.
It's really a tensor.
So that's really a 3 tensor.
Yeah, it's a 3 tensor, one of the short dimension.
That's correct, and I single out the dimension that corresponds to these dangling edges, so that when I fix them to some particular value I, so if I look at the corresponding slice, I get this D by D matrix, and I have this nice representation as just in terms of a product of matrices. The only reason I wrote in this asymmetric way was that I could sort of relate to this name matrix product state. And it's really because essentially the components of this tensor are given by traces of products of matrices. Here, I guess they're rectangular at the end. Just some special case, if this D is 1, then nothing happens here, right? That's just a tensor product of rank 1 things. So these are tensor rank 1 objects, or I guess some degree variety. If we've only 2 of these sites, then what we're really dealing with, so suppose we only have 2 of them, like this, D, D, D. Then we're looking at a little d by little d matrix whose rank is bounded by capital D. Okay, so these are sort of these classical objects. And you could think of this as a generalization, right? It's generalizing tensor products to some slightly higher rank. And so, but the rank is enforced locally. It's not like a global bound on the tensor rank or something like this, naively. Okay, so that's that. Good. So these are these matrix product states. What's the time? Then another thing that so now naturally so this is something that we will later see is useful for describing physical systems in 1 dimension on the line. Okay, and there's a 1-dimensional graph. So naturally there will be a 2-dimensional object. It has another name, which I will not.
To this to be visible, you should pull the bottom.
Then I think we will not need this anymore, but maybe I can just erase this then. So this was my sort of the attempts that we will not pursue today. So let me erase this. This will need. And so now I'll add these. I'll look at the 2D version of this thing. So this is often called PEPS, which is projected entangled pair states, I think. So this is a reason that's a name that's not so important right now. But it looks exactly the same, but in 2 dimensions. So you have pictures, right, basically that look like this. So you have these. You have like a square lattice, for example, of tensors, and then there's like these legs sticking out to the bottom. So this, so say again, the ones that sort of stick out to the bottom are little d-dimensional, and the ones in the plane are, say, capital D-dimensional. So that's exactly the same. Does that picture make sense? So it's exactly the same thing as here, except in 2 spatial dimensions. And so such a thing describes an element now of CD, say, tensor nx times ny. If you have nx lattice sites in the x direction, ny lattice sites in the y direction. Okay. And again, clearly these are few parameters as long as this capital D is not large enough, and it's something people like to use for 2-dimensional systems. Now, let's try to see sort of more specifically. I mean, let's look at certain ways by which these particular families and also general tensor network states deviate from being generic. And so, yeah.
Just to make sure, I mean, you gave the example of just a low-rank matrix if capital D is smaller than big D. But in general, big D could be bigger than little d. Or it's
That's correct. No, you're totally right. Yeah, you're totally right. So you could ask, how large does this capital D have to be so that actually you capture all tensors? And then you'll see, okay, this one, for this one, D squared is enough. Now this one has already to be larger, because the rank of here cannot be d squared, so maybe this is, I don't know, d to the fourth. That's correct. That's right. And so you'll find that, of course, this capital D has to be exponentially large if you want to capture all tensors in this exponentially large space. But there's typically, so in the situation of interest, little d is just some fixed thing, like 2 or 3. And this capital D, we hope, grows only polynomially with the number of sites, and then we'd be happy. And we'll see later that theorems exist that tell us that this works in certain situations. Good. So let's look at sort of, let's look some more into ranks, okay? So one sort of measure or diagnostic by which we can see how these states differ from generic states is by looking at ranks or flattenings. So flattening of a tensor is basically, you have a tensor with many indices, you group the indices into two parts, A and B. You think of the whole thing now as a big matrix from the A indices to the B indices, and you look at the rank of this matrix. So that's sort of the pedestrian definition of the rank of a flattening. So let's do this. Maybe I'll, well, okay, this will involve some walking, but let's look at ranks. So ranks of flattenings. So suppose we have some tensor, say an arbitrary tensor in CD tensor n. We'll write the set 1 to n as some, we'll choose some subset, or we'll write this as A union A complement. Now, corresponding to this, we can consider what's called a flattening, which would be, I guess, conceptually speaking, well, never mind. So first, it will be a linear map from A to B, from A to A complement. Again, everything is in coordinates, and I'll not write down duals. We can ask what's the rank of this linear map, okay? And that's something that, of course, in general, we can only bound by the smaller of the two dimensions. Okay, so the rank of this flattening TA is at most d to the, say, minimum of the cardinality of A and of A complement, okay? And clearly, generic tensors will saturate this. So now, suppose we look at the same quantity, but for one of these tensor network states, maybe for one of these matrix product states over here. And so suppose we have some subset of these legs, right, of these n legs, maybe this one, maybe this is A. And we ask, what's the maximum rank of this flattening? So while I walk over there, okay. So say in such a matrix product state, if A is such a contiguous interval, well, the tensor sort of gives, this tensor network gives you basically factorization of the tensor, right? And the factorization is basically mediated by these two legs, right? Because if you cut them off, then you disconnect the tensor. So whenever you fix these values, you're good. So there's two of them, and so the rank of this thing will be most d squared. Right. So rank J. Because basically the network, the graph itself gives you a certain decomposition of your tensor. Adapted to this thing. Okay, so that's good. Similarly, how about these PEPS states, these PEP states?
But you don't have to do it contiguously.
I do not have to do this contiguously, right? So suppose I have two intervals. Maybe this is also part of A. Well, maybe not this. Maybe this is also part of A. Then in this case, I could still say, let's cut sort of the edges adjacent to this block. Let's cut the ones adjacent to this block, and so on. So in general, what you would look at is you would sort of look at the boundary of A, so the edges that leave A, each component of A, and then sort of each boundary leg gives you one thing in the exponent. So you look at the size of the boundary, and you get d to the size of boundary. This is sort of more transparent even in this two-dimensional picture. So suppose here we look at a subset of these indices. Well, let me make this slightly larger so the network continues on and on. Maybe I care about these indices, okay, or some larger region. Then, okay, naively, I get a bound on the rank which is little d to the number of sites. But if I run the same argument, I can instead cut off the network like so. So along these edges that leave region A. And I'll get a bound on the rank, which is good if the region is really large, because it only scales like the boundary of the region, okay. So find rank TA less or equal to d, and maybe I'll, how did I call this? Maybe I'll call this gamma A, and gamma A is this particular cut that I chose here. Maybe this thing I call gamma A. And because all of these bond dimensions are capital D, I get the bound I wrote. Okay. And the general picture, I guess, is now clear. So whenever I have a general tensor network state based on some graph, and I look at the I want to bound the rank corresponding to some flattening, then what I should look at is basically at a minimal cut between A and A complement. But I want to weigh this cut. The weight I want to give is the product of the bond dimensions that I'm of the dimensions of all the edges that I'm cutting. So in general, so our usual setup, right? We have some graph, some tensor network state T and S, some graph G, and so on. G has these two vertices. These dangling legs on delta, so we're going to split up delta into A and A complement, so disjoint union. And then what we can do is we can bound the rank of TA by the minimum over all cuts, and then whenever we have a cut, we look at all the edges that we are cutting and multiplying the bond dimensions, and we want this guy to be a cut between A and A complement. Okay. Good. So that's that. Okay. Good. So similarly to before, under mild assumptions, this is going to be tight for generic tensors. That is something that has been dubbed the quantum max flow min-cut theorem by Cui, Friedman, and others who looked at this. And the mild assumptions are, for example, that all these dimensions are powers of some base, say 2 to the something. Then you can apply basically classical max flow min-cut. So this is tight for generic, say, tensors Tx. Say under mild assumptions. This is Cui, Mike Friedman, and friends. Okay, Orsatat, Stong, and Minton. So yeah, I guess if you want to know more about other kinds of ranks, non-bipartite ranks, you should ask Visu, who told me yesterday that he thought about this. So that's nice. But now if we bound ranks, we can also look at sort of more quantitative measures. So ranks are very coarse somehow, right? They're not very stable. If you perturb your tensor, it will go up and so on. So typically, just the fact that this rank is not very large should not concern us so much. We could also look at something that's a bit more continuous, like an entropy. And so entropies are also of interest otherwise. Typically, entropies, reasonable entropies will be bounded by the log of the rank. So the same upper bound will apply. I should actually say, so this bound is an instance of what is called an area law. Area as opposed to volume, the log rank is basically bounded by the area, by the size of a minimal cut, by the boundary area instead of the number of sites in A. So we could also ask the same question for an entropy. For example, we could use, in here, maybe I should briefly define what kind of entropies we're looking at. So because we have tensors and quantum states, we want to look at quantum entropies. Let's look at the family of Renyi entropies, quantum Renyi entropies, which are parameterized by some parameter alpha. So the general definition of the alpha Renyi entropy of some quantum state is as follows. So how do we specify quantum states? In general, they are specified by PSD matrices with trace 1. We'll see in a moment how such a row arises from a tensor and a choice of A. That is from a flattening. So if we have such a density operator, so that's like a non-commutative probability distribution, right? The eigenvalue is formal probability distribution. Then the Renyi alpha entropy is hopefully defined as follows: 1 over 1 minus alpha log trace rho to the alpha. Okay. So this is monotonically decreasing as we increase alpha. For alpha equals 0, we basically get the log rank, right? Because that's sort of the meaning of rho to the 0. For alpha equals 1, we get what's called the von Neumann entropy, which is just a Shannon entropy of the eigenvalues. For alpha equals infinity, we get something like minus log of the largest eigenvalue. So that's the smallest of all these entropies.
Sometimes called the min entropy in the class.
That's correct, yeah. So alpha infinity is min, I guess alpha 0 is max, or yeah, depending on the definition. That's right, yeah. And so somehow, let's say they are in alpha. So how do we, excuse me? Rho is, yeah, sorry, yeah, by this I mean PSD matrix. So this will be some PSD matrix with trace 1. Then we can define these entropies. Now the question is, how do we get a PSD matrix from our setup?
No.
Yeah, but
I'm
that's
just wondering. So you're taking rho to the power alpha.
correct.
And you want these alphas to be positive integers, or you want them to be
Yeah, so let's say they're in this range.
except for 1?
For 1, if you take the limit, you'll also get a good definition, and you get this for alpha equals 1. You get this what's called the von Neumann entropy, which is minus rho trace rho log rho. So there happens to be a good extension to 1, and as well as to 0 and infinity.
It would be like
Thanks.
general entropy. All this was done
Yep.
first classically, Renyi defined.
So these.
Classical,
That's right. So these are exactly the classical Renyi entropies generalizing the Shannon entropy for the eigenvalues of rho, and the eigenvalues form a probability distribution by this assumption. Thanks. So now, okay, I want to construct such rows to which we can, so that we can measure this entropy. So let's do this. So if we have a tensor T, say in the general scenario as above, and we have such a subset A, and let's suppose this tensor is normalized for good measure. So the norm square of T is 1. Then we can define an operator rho A, basically precisely by taking TA star TA, right? So TA is a linear map from A to A complement. If I multiply it like so, I will get a map from CD tensor A to CD tensor A. So it's an endomorphism. It's positive semi-definite because it looks like so. And it has trace 1 because this tensor T is normalized to norm 1. So that's a particular object to which we can apply this definition. This is called the reduced density matrix of a quantum state described by this tensor to region A. Okay, that's the lingo. So in physics, it describes the state of a subsystem. Sometimes we also call it the quantum marginal, because it's like marginalizing a probability distribution. Now, sort of trivially, because any of these alpha entropies is bounded by S0 by the log rank, we get a similar bound. So that is something that's maybe more commonly known as, so usually we state these area laws for entropies, but it's just a trivial consequence of what we said above. So by what we said here, we can bound S alpha of rho A, right, by log rank rho A. And now I guess I just have to take the log in the right way. We do the same minimization, but now we're summing E and gamma A. We take the log of the bond dimension. And so that's maybe a slightly, so same minimization over cuts between A and A complement. That's maybe slightly more pleasant, because if you imagine that these bond dimensions are all the same, right, you get something that's proportional to the number of elements that you're cutting. So that's maybe, so that's linear sort of in the size of this area, volume of this area. Okay, so now you could again ask, is this saturated for generic tensors? Maybe that's now a more quantitative statement. No, that's right. This was a weaker statement than this bound, but of course, if you show that that's approximately saturated, it's going to be a stronger statement that's showing the same for the ranks. And one way by which you can do this, you can sort of, so this is going to be true if you choose your tensors at random, for example, Haar random, and you look in the limit of large bond dimensions. But in order so that this geometric picture is the same, you should scale all these bond dimensions and appropriately. So maybe you take them all, right? Sort of basically the log. You imagine that the bond dimension is something like, I guess, say dE should be maybe something like d to some CE, I guess, and then you let d become large. That would be sort of a legitimate thing. That would be a good limit to take, because then you would sort of preserve the ratios of these logarithms. But you
don't you expect this to be true for d equals 2? Why not?
Let me think. No, I think in expectation these things will be true, but if you want sort of some fluctuations, like if you want some with high probability statement, then the dimension has to be a bit larger.
Not just high probability, just that some generic tensors have this maximum.
This would be probably. I think this may be true. Like if you just I think that's probably right. Yeah. I mean so we were interested somewhere in the stronger statement if you choose them at random from a particular ensemble, because then like in some applications we would need this for many A's at the same time, and you want to use unit bounds and concentrate things. So let me maybe say the stronger statement. So if you choose them at random from say the Haar ensemble, then this is true. up to some over 1 corrections in this limit of large bond dimensions for random. If you choose these tensors randomly, that's something we did with Patrick Hayden and friends. In some specific context, which sort of relates to last week's conference, but it's maybe not so important here. But it's basically a way of constructing. It's like an interesting random ensemble that gives you some geometric meaning, right? Because you still have this graph to play with. So it's a way of constructing certain quantum error correcting codes that have some interesting locality properties, because you can play with this graph. So that was sort of our motivation. But that's maybe a bit of an aside. So maybe, okay, just to summarize. So we only looked at this. We looked at sort of these 2 measures, right? The rank and the entropy. One maybe being a bit more stable than the other. And sort of the key point is basically, is that you pick your graph, you get a set of tensor network states, and they satisfy such an area law. So roughly speaking, you can only hope to approximate a quantum state by such a tensor network state if you choose the graph in such a way and the dimension in such a way that you have the capacity of reproducing this entropy. That's sort of a priori and maybe an imprecise statement, right? But that's sort of the intuition that people have. Sorry. Right. But there are some converses actually. So in 1 dimension we know that a converse. So in 1 dimension we know that sort of on a line, if the area law is satisfied, say for some Renyi entropy with alpha strictly smaller than 1, then you will be able to approximate your tensor by matrix product states of sort of only polynomially large bond dimensions, say. So there are such converses. So maybe I can so roughly speaking, neat area law. If want to approximate some given tensor T by some tensor network state, and in 1D it's sort of an if and only if. So this is very vague, but sort of I think that maybe
Talk more about this.
I will come back to this, yeah, in more precision. Yeah.
The way I understand the area law is that the other direction. I mean, you have an area law if you can match or approximate.
So that's right. That's correct. That's kind of what we discussed. The other
result is proving an area law.
That's right. And I will not go into the proof of this, but I will say in more precision what is being proved there in the corresponding setup. But sort of historically, so I mean, we'll talk about this local Hamiltonian business later on, and then people were trying to prove that the ground state of these models could be approximated by a matrix product state. And the first route by which this sort of worked out was by Hastings' sort of celebrated proof of the area law. And then it implies somewhat straightforwardly, as was sort of previously explained by, I think, Verstraete and Zirac, that you can actually approximate by matrix product states. I think a similar, that's right. But it's sort of using this 1-dimensional structure. You have a left and a right. You can do some recursive or inductive construction of your matrix product state. But that's sort of, maybe I'll come back to this in a sec. Yes?
When you use the term 1 dimension, the 1-dimensionality thing is the fact that you're in a chain?
Yes, for this statement that satisfying the area law,
just where you're clipping it, you have a 1-dimensional chain, you're clipping it.
That's correct.
It's not that 2-dimensional lattice thing.
That's correct. That's correct. That's what I meant with 1. Yeah, you're right. Yeah.
But you're right. It's not known for trees, which can also be cut by 1 edge. Tree can be thought of as 1-dimensional.
Yeah, I think sort of the
mean cuts are 1, and such a statement is not known for.
Right. Good. So this is this. Oh yeah, maybe I should say, okay, this is extremely rough and superficial. So I mean, people know more sort of structural properties, I guess, of tensor network states, and I guess there's a lot of intuition in the physics community about which networks match which states. So we'll come back to this, but what is known as gapped local Hamiltonians are believed to be well approximated by such networks. Whereas for critical systems, so systems at a phase transition, we believe that these bond dimensions have to become larger, and/or you should use different kinds of networks. So for example, you could, so here it was sort of maybe natural, but it was a coincidence that the dimensionality of the graph, right, the intuitive dimension of the graph was the same as the dimension of the states that we want to approximate, right? Here we had a two-dimensional lattice on which our Hilbert space was built, and then we put a graph on top. But no one tells us that that's the only way of doing it. We could have like a three-dimensional structure describing a two-dimensional object. And this will, of course, in general, increase the expressiveness of this ansatz if we use the same bond dimensions and so on. So that's something one could do. So for example, there's something called a MERA, which is, again, an acronym inspired by what's called the renormalization group. So it basically describes systems where you have correlations at all scales. And so it makes sense, even for a one-dimensional system, to have sort of a decomposition of your state into sort of, correlations at a certain scale, then at sort of twice the scale or 4 times the scale. So it's sort of a self-similar network, similar to, say, these convolutional layers and neural networks, if some of you work in this. Right, so it's basically like a fine or coarse graining procedure. So that's something one can do. And those, of course, they would satisfy different kind of area law. It would not be this one-dimensional area law where you just get a constant for each connected component, but maybe some logarithmic growth of entropy, which is known that these to be satisfied by these systems. So maybe I'll say some more word of this. Okay, so now we have this zoology of tensor networks. Maybe we can talk a bit about sort of operations that we would like to perform on tensor networks.
So Michael, when it's convenient for you, you can take some 5-minute break, and maybe the audience will thank you.
Would the audience like to take a 5-minute break? I mean, it might be a good time now. So basically, plan for the rest is I want to talk a bit more about what are the operations that we want to do with these networks. So mainly to contract them. So we should talk about when is it easy, when is it hard to contract a tensor network. So we'll see in one dimension it's easy. In general, it's sharply hard. For even for tensors that have zeros and ones, we'll talk about this. And then we'll come back to these sort of physics-inspired ground state problems, and I'll briefly say what is known there. So maybe we'll reconvene in 5 minutes. And well, it's camping on the door. Okay. Yeah. Maybe I'll just continue for a little longer. So next part, we want to talk a bit about the complexity of doing certain tensor operations. So I hope I only erased the right thing. So these were our two sort of instructional families of tensor networks, these matrix states and these PEP states. That was the general setup. And I guess here is this area law on entropies that will reappear later. But let's briefly return to the general situation. So maybe this is called computational complexity. So here, suppose now someone hands you a tensor network, which is internally composed of contracting many small networks. So it's somehow efficiently representable, right? So there's all these like tensors here and some contractions and whatnot. But in the end, this is just some box, right? You all put them in a box, and out come a certain number of wires, which are these indices I1 to In, corresponding to this Hilbert space, this vector space. And so now you could ask, okay, what are the kind of operations that we care about, that we want to do? So I will suppress, this internal structure. This is just my cartoon. But inside this black box is a tensor network. So you know that you can represent this thing efficiently, right? Say it's not very large. So now it turns out that most things that we want to compute about these tensor network states are actually basically boiling down to computing norms or norm squareds. That is basically evaluating a tensor. So if you have such a box, a tensor network that does not have any dangling edges, this corresponds to a scalar, as we discussed before. Like for this matrix multiplication triangle, when you plug in specific matrix A, B, and C. So here there are dangling edges, but sort of I claim that most interesting examples boil down to situations where we don't have them. So maybe I'll write this down. So most tensor network sort of questions that we ask and most computations that we care about reduce to what is called contracting a tensor network that does not have these dangling legs. Contracting a tensor network, I don't know, state is maybe a misnomer, with delta equals 0, right? Delta equals empty set. So this corresponds to a scalar. Just computing the scalar. Okay, computing a scalar. So the prime example, of course, is this norm, or norm squared, which you may, for example, try to compute in order to determine whether this thing is zero at all, non-zero at all. So pictorially, okay, what do we have to do? Well, we take our tensor network, and then, so this is sort of a vector. Now we need the corresponding covector. We can just obtain this by complex conjugating all these tensors, which maybe I will suppress, or maybe I'll write this as tensor network state. Maybe this I'll write as tensor network state complex conjugate. I just hook them up, right? And that's an inner product between the vector and the corresponding covector. And this is a tensor network without any dangling edges. So that's exactly the situation. So that's a particular contraction.
You didn't compute anything yet. You just
I'm just expressing. So I'm only sort of trying to explain this reduction in a way. That's right. And then we'll see how to solve such a problem, or why it's hard. You could also ask, right? I mean, sort of the thing that we said before is maybe not so interesting in general, but we could also ask for specific components of this tensor, right? For example, say the ti1 to in component. Well, clearly this is just obtained by taking this same tensor network state from above, and here we're sort of contracting with the first basis vector ei1. ei2, right? This is, I guess it's a sort of a trivial way of doing it, but I'm just saying this can be done. What's mostly of interest in physics is, well, it's basically this norm squared, because in general these things will not be normalized. And then expectation values. Expectation values of so I'll say what this means mathematically in a sec. Expectation value of local observable, which means operators that only act non-trivially on a few of these legs. So maybe I'll first write this down pictorially. So expectation values. So pictorially, okay, this is not going to work, sorry. What I want to do is the following. So I want to take my tensor network state. Let's make this a bit wider. And then I want to maybe, so I have all these indices here, all these tensor factors. Now I want to apply a linear operator to one or a few, in general, a few of these legs, maybe just one for simplicity, maybe an operator A. This is going to be a matrix, so I get another leg back. And I want to contract this again with a corresponding covector. Okay, so I want to look at a picture like this. So this is Tina's. I'll often omit these complex conjugates, but you'll catch me if I do. So what this computes mathematically is basically the following. So we take this tensor corresponding to the tensor network state. We are applying basically something that's a tensor product of many identity operators. Identity is in all of these other indices, except that sort of at one of sort of the location x corresponding to where this operator acts. So something like many identities, A, and more identities on the right, or on these other things. So I draw this in a one-dimensional line, but of course this makes sense in general. Maybe I'll call this guy AX. This is an operator, supposing that this is sort of the xth location. This could be an integer, or it could be a particular vertex in delta. Okay. In general, so we're interested in these things. More generally, we're interested in such expressions where we insert not only one, but a few of these operators. So, a related quantity would be something that's called a correlation function, two-point function, which is pictorially tensor network state, and then maybe here we apply an A, and then somewhere else we apply a B. And that's a bit like sort of a, something like when you compute a covariance, say, right, you have this expectation value of x times y for two random variables. That's basically the quantum version of sort of a mixed, well, I guess it's not a moment, but so the sort of the mixed, the part where you don't, in the covariance where you don't extract the means, the product of the means. Right, this is like roughly something like an expectation of A acting on side x, B acting on side y, right? That's sort of the quantum version of this. So these are things that we like to compute, but you see sort of even from picture, these are all contractions of tensor networks without boundary legs. Okay. So how do we do this then? How do we solve? How if we can do this? How do we do it? So how to compute?
When you say to compute, the input is actually the values of the tensor.
That's correct. That's correct. So that's right. So say the input is really, so you could imagine maybe there exists a universal contractor that gets this input. Maybe, well, either we fix some family of tensor network states, we just input tx, or maybe this entire description. Say this is a polynomially large description. Can I compute this contraction? Okay. And so now I want to restrict my family indeed, say, to matrix product states, and then we will see that you can do it. And then we'll talk about how in generally it's really hard to do. And so in the case of matrix product states, say the input would indeed just be the tensors t1 to tn, and so remember from here that those things we could just write as follows. But the input would be a classical description of these tensors. And so, well, how do we compute this norm squared here? I'll just draw exactly the picture that we drew here. Okay, this will be the contraction of this network. Now, what I should not do, of course, is I should not cut this like this, compute the quantum state in this big Hilbert space, and then compute this inner product. What I should do instead is sort of doing inner product in this direction. So what I should do is I should think about this thing as a vector in a d squared dimensional vector space. Then let me fix up the picture a little bit. This thing I could then think as an operator. Different color. This thing I could think as an operator. These are the inputs and those are the outputs. I simply apply this operator n-2 times, and then I get a vector in CD tensor CD, and I take the inner product with this thing, this boundary vector on the left-hand side. So that's going to be the approach. Okay, and it's exactly just iterated matrix multiplication by basically the tensor corresponding to this thing, and sometimes it's called a transfer operator and the lingo. So maybe I'll just say this pictorially. So really what we're doing is we're sort of taking the inner product between this vector and CD tensor CD. Then we're taking a power of this operator, so the n minus second power, I guess, and we apply this to this vector.
That's when they're all the same.
Right, yeah, sorry. Yeah, you're totally right. Yeah, so I guess I was too quick here. Let me postpone this by 2 lines. Yes. So I should say this separately. Thanks. So all of these things I can think as operators. So these are all sort of CD squared to CD squared operators, and I just multiply them. So I guess I need d to the 2 times omega to do so, but certainly you can do some polynomial time, and I get the answer. So this we can do. And often there's some interesting, so this is an interesting object on its own right for several questions. So I guess we can just say this is sort of something like order n d squared by d squared matrix multiplications. So that's often quite doable.
In the case that the one-dimensional thing is actually a loop, so it has to kind of come back on itself, sometimes in these sort of partition function calculation things, that matters, or it's different, or...
But it would be a trace instead of multiplying on the left and on the right by a vector.
So you'd just be calculating the trace.
In this particular case, it will be fine. Indeed, yeah, you would sort of just calculate the product, and then the closing it up will correspond to the trace. That's right. In 2 dimensions, of course, all these things are much less clear, and things are hard, as we'll see momentarily. But in 1 dimension, we're good in both situations. Thanks. So I guess it's clear that now we can of course use the same strategy for, say, these expectation values and so on. We treat those things all the same, and here we just have to insert this one operator. But if we don't have too many of these operators floating around, I guess even if we have one everywhere, that will be. That's even simple. Yeah, you have enough time to do everything. Yeah, that's right. So that's all simple. So that's great. Yeah, so now maybe I can briefly say what we said before. So this will be somewhat heuristic and sloppy. So suppose that this is, yeah.
It's that simple. I mean, these are operators. This A and B are operators on the little d dimensional space.
Yes.
But if you have to insert different ones in every, don't you sum over all of them? Maybe it is important that you are doing just a constant number.
No, I think you could still build this object, I think, as a building block, as an operator, and then you insert.
It will be another divided
Yeah, that's correct. Yeah, I think you're right. I mean, I think that's fine. Yeah. It would only be an issue if you really acted on a lot of sites, but then I guess also your input is pretty large, depending on how you specify A. Let's briefly look at a situation where all these tensors are the same. Where all these tensors are the same. Sometimes that's called a translation invariant matrix product state. In particular, in this cyclic situation, then you really have a shift symmetry. All t, I guess I called them tx before, or t lower x, I'm not sure, are same. So then there's this interpretation of just taking a power of the. Then I have sort of a unique a single such operator, right, which is the same for all sites except the boundary sites or the sites where insert some operator A or B. So it's sort of interesting to look at this object. I'll just insert these arrows to indicate directionality. So what I'll have to do is I'll have to do things like this, right? So some power of this so-called transfer operator. And so suppose this transfer operator is diagonalizable, and it even has, say, some spectral gap. Then it's sort of clear what happens if we take high tensor powers, right? Sort of this will sort of quickly we'll get something that's roughly a projection on the largest, on the eigenvalue correspond to the largest, on the eigenvector correspond to the largest eigenvalue, or on this left-right eigenvector pair, whatnot. No, on the eigenvector, in fact. Sorry. And so what it means is that if we have a correlation function, which I'll just draw again here, which kind of looks like this. So we have some A. So then we have many of these things. Maybe say the separation. So this is side X. Then maybe you have a B on side Y. And we continue over here. Say the separation here is K sides. Then we would be led to computing such an operator here in the middle. But if this gap assumption is satisfied, you're essentially decoupling the left and the right hand side of your chain, right? So maybe I'll be somewhat sloppy. So if diagonalizable, right, we can sort of think about this as some, I don't know, whatever, G inverse to the K, right, which is somehow G d to the K. G minus 1. So if we have something like maybe I'll just say a spectral gap, and maybe I normalize the largest eigenvalue to be unity or something like this, then basically this is right something like GV. Maybe the first eigenvalue is the largest one, right? Then I have something like E1 star G inverse, and so this is really somehow a vector times a covector, right? So pictorially this corresponds to something like some state here times some other state here. So what I'm saying is sort of you're sort of rank 1 as K becomes large. The left and the right decouples. So what follows is that this expectation, or this correlation between A and B is roughly the product of the expectation value of A times expectation value of B. In other words, if you look at something like the covariance, this will go to 0 very quickly, or the correlation will go to 0 very quickly, and will go exponentially quickly, basically if you have the spectral gap assumption. So this is maybe let me write down what I mean mathematically, then we'll come back to the picture. I guess there should be some approximate, and this approximate will be true if we have a spectral gap and K is large enough. So we'll find something like this, that let's remember the notation. So before I wrote AX for the operator that acted non-trivially on side number X and by identities otherwise. So that's such a correlation function I can write as AX times BY. as the expectation value of ax times by. So this is the thing that's calculated by this picture. And now I want to compare this with the expectation value of A alone times the expectation value of B alone. And to have this interpretation as expectation values, maybe I want to normalize my tensor to have unit norm just to avoid trouble. Otherwise, I could divide appropriately. So the statement will be that somehow this difference will vanish exponentially. And there will be something of the form, something like this, I guess. 1 minus, did I say spectral gap delta? To the x minus y, I think. So something like this. Maybe there's some constant somewhere, so maybe I'll be a bit careful, and maybe I'll add some constants here. But roughly speaking, I think these no, maybe I'll not write this. Roughly speaking, something like this should be true. So there's sort of an exponential decay in these correlation functions as you separate x and y, if these conditions satisfied, right? If you have the spectral gap diagonalized and so on. And so that's sort of, something, something that is called in one form or another. So maybe don't hold myself accountable for factors that are missing here. We call this exponential decay of correlations. And so in a sense, it's a consequence of this matrix product state ansatz, provided you have this gap. And you could again ask for the converse. Suppose you know that exponential decay of correlation holds. Can you then find a matrix product state approximation? And if one, in a 1D system, still, that's right, that's crucial. Say in a 1D system, which is sort of also where this notion of distance comes from. Suppose you have such a property. Can you then prove that there exists a nearby a good matrix product state approximation? And this was believed not to be true for a while, sort of because, for example, there's quantum states that are very entangled, but they have small correlations. But somehow, if you demand this property sort of in a somewhat stronger way, sort of not only for these single points, for say a fixed single point, but sort of for arbitrary ones, and also for larger regions and so on. So maybe I should not go into details. You can actually prove that it's enough. So this is something that was shown by Fernando Brandao, and Mikhail Horodetsky. So there's sort of a converse in 1D. I guess everything on this board was in 1D. So exponential decay of correlations. I'll just say again in 1D implies sort of the existence of MPS approximation.
So there is a particular this way the exponential decay of correlation is to assume you really have some quantum system in mind, and you want the graph to be identical to the local connections in this quantum.
Yeah. So suppose I have a one-dimensional graph, maybe on a cycle, and I have a particular quantum state, and it's true that whenever I have, and I put two regions. Okay, maybe I should let me add more of these things. Suppose I have one region A and another region B, and now suppose that the generalization of this expression, the sort of covariance, for any operator supported in here and operator supported in here, is exponentially small in this distance between these two regions. So that's a bit more general. I don't look only at single points. Then let's call this exponential decay of correlations, and the exponent would be this psi, and we look at the minimal distance. If you have this for all pairs A and B of regions, then it implies that there exists a matrix product state of small, I'll say in a second how large bond dimension, that is a good approximation to the state you started with. So you don't need a Hamiltonian for this, but you need a state that satisfies these kinematic properties. So if T is an arbitrary tensor that has this generalization of this property, you find a tensor T prime. That's a matrix product state, which is nearby.
And this is independent of the one dimension we know in our quantum state. I mean, you might as well have been given one tensor network with very large.
Yeah, that's right. Yeah.
This, and you say you can approximate it by one with low.
Yeah, that's right. And so somehow the way that D scales is it's somehow exponentially in this correlation length. I think sort of that's what Brandau and friends prove. So I guess something like some up to some log. I mean, I think this is true up to some log factors and stuff. So I guess in this case it's something like 1 over the gap. But I mean, this is of course derived from the tensor network. But suppose you had something like this of this form. So that's the relation. Okay. Yeah. So the correct technical way of interpreting is it's a stronger statement than this one, right? You have it for all these regions. What replaces the distance? You look at the minimal distance, but sort of either this or this, say, on the circle. And if you have this exponential decay from psi in all these regions, you get a good matrix product state approximation. But this bond dimension that is not the physical one, so the bond dimension here, this was d, is that large. I think that's roughly the Brandau. I guess I didn't write down people's names, which I should have. So it's Brandau, Horodetsky. Okay, so that so far is the reason I mentioned this is now we sort of have two of these converse statements. One is an area law implies nearby a good matrix product state approximations, and exponential decay of correlations apply one. So historically, this converse statement was, I think, discovered after Hastings had, well, both, I think, established exponential decay of correlations in certain gapped one-dimensional systems based on sort of ideas from mathematical physics, Lieb-Robinson bounds, and so on. And but then some of this was not clear. So he first had to prove this area law to get a good matrix product state to prove that there exists a good matrix product state approximation. And I think it was only later discovered that there was also this alternative route. So that's sort of two criteria in a way for proving the existence, not for finding, for proving the existence of a good matrix product state approximation.
One is the weaker than the other.
I mean,
any one-dimensional system has an area law.
well, that was to be shown. I mean, if you know it comes from a matrix product,
You're
yeah.
talking about the converse.
Yeah. That's right. Okay. Yeah, so now this looks great in one dimension. So how about higher dimensions? Of course, there generically things are hard. And so basically contracting an arbitrary. So I guess there are quite a number of works that sort of explore the richness or the computational hardness of contracting tensor networks.
One may want to pull the other
Should
one.
I? Well, let's see whether it's a. Yeah, maybe we'll leave this one actually. Perhaps we will. Oh, I guess yeah. Excellent. Got some space. Yeah. So, in general.
Before you leave one dimension, as obviously mentioned, are
Yes.
trees at all something that one understands anything about?
So I think not sort of to complete satisfaction. So I don't. So the ultimate sort of theorem that I'll talk about in the end will be one that shows that we can actually find in polynomial time these matrix product state approximations for certain one-dimensional systems. And I think such a theorem is not known for trees.
It's known only for a line, as far as
It's only known for a line, yeah.
I think nothing, even the existential part is not known for.
I think not. I'm less sure, but I think it's not. I think, like, of course, if you have a tree, you can derive lots of structural properties that are very similar to what we discussed. But I think these converse statements, I don't know they are known. So, yeah.
So the area law, the spectral gap was thought about in terms of this transfer operator, or was it the spectral gap something with Hamiltonians?
Yeah, so here it was the transfer operator and what I write here. But when I said gapped local Hamiltonian all the time, I was referring to Hamiltonian, so that's very confusing. I'm sorry. So here, sort of. For the purpose of this bound, this was more to establish that sort of generically you would expect from matrix product states to have an exponential decay of correlations. So again, you could only hope, if you have a physical system, that's a very physical assumption, a physical property. So for a physical system where this is not true, maybe those are a bad ansatz. So I mean, there's some caveats because, of course, generically you don't have to have the spectral gap, but okay. But we'll come back later and sort of discuss actual Hamiltonians, which also have a spectral gap, and that's something more physical. And this, for this class of Hamiltonians, basically both exponential decay of correlations one can establish as well as an area law. And so we can use either of these two converses to see that there must exist a good matrix sparse state approximation. Then the question will be how to find it. We'll talk about this in a bit, I think. Maybe I'll be very short on the sort of complexity side of thing here. So in general, sort of you could look at these two problems given, as input a tensor network, either restricted to a family such as PEPs, or just an arbitrary graph, one dimensions and these tensors Tx. Is this thing 0 or not? 1, 0 or not? Or you could ask, actually, what's the norm squared? Let's compute the norm squared. And maybe we could restrict to sort of to the case where these tensors has only entries that are 0 and 1, right? Then this is an integer. We can think of it as you can try to put in some counting class, for example, or prove some hardness. So suppose all these Tx's have entries in 0 and 1. But we don't do arithmetic mod 2. It's the ordinary arithmetic, but I'm just restricting to integers. And then this norm squared will also be an integer, and we could ask, what's happening here. And so here, I guess this thing is, so yeah, maybe we'll assume both of these properties, actually, for now. One can do various other things. One can look at it mod 2, and people have done this, but so this is the scenario I know best. So this will be NP hard, and this will be sharp P hard in general. And basically, I think there's a simple proof. For example, you want to suppose you want to reduce circuit satisfiable, counting the number of satisfying solutions to a set or to a circuit set. You can basically easily construct a tensor network corresponding to a Boolean circuit, and you can choose certain. So this will be right, like you have your circuit as in and outputs, so your tensor network has in and outputs. But then you can sort of contract it with certain states such that you exactly count the number of solutions. And so basically, it's so simple, I think, so that we can try to do it. So suppose we have some Boolean circuit, so say some gate. Okay, so maybe it has 2 inputs and 1 output. Maybe this x1, x2, and y. So these are bits, right? These wires. From this, we can construct a tensor where all these dimensions are 2. So these bond dimensions are all 2, right? So again, it has 2 inputs and 2 outputs. Maybe I'll, I don't know, make this sort of a fat line to distinguish it from the gate we started with. And this tensor will just be, sum over x1, x2. They're both either 0, 1, ex1, tensor ex2, so the basis vectors, e f of x1, x2, right? So that's a perfectly good tensor. And now, of course, if I have a circuit, I can directly and efficiently translate this into a tensor network. And so let's do this. So if I have a Boolean circuit, this will give me a tensor network, or tensor network state, if you like. And so now suppose I want to know the number of satisfiable inputs for which I get 1. Okay, so then let's do this. So number of satisfying inputs. How do I compute this? Well, I take this big tensor network state, right? So this is going to be something. It has, if my formula is, my formula is 1 output, but in general there's many inputs, x1, x2, xn. Sorry, my circuit. So here in the inside is now the tensor network that's corresponding to my circuit. So how do I get a number out of this? Well, what I could do is the following. Let's plug in certain vectors here. I'll call these vectors plus. Plus is the vector that's just e0 plus e1. That's a nice vector, right? Now I'm basically summing over all these 2 to the n options. And here for y, I guess I'm just maybe projecting on the one basis vector. And then this should, if I didn't make a mistake, just give me the number of satisfying input assignments or inputs to the circuit. And so that would be one way of seeing why this should be tricky. I think even if you restrict to something like PEPs, it will be a hard problem. Because you can, for example, you can encode classical partition functions. Basically an arbitrary classical partition function of some local classical Hamiltonian. You can basically encode in this fashion, by constructing corresponding tensor network. So yeah, you can put any graph.
In a grid of slightly quadratically
Yeah, that's right. Yeah, so you could say these are like very, very unphysical circuits, right? Circuits are very unphysical objects. But even if you look at a regular grid and you take some hard partition function.
If you allow a blow up of the quadratic.
Yes. Yes. Yeah, that's right. That's right. Yeah. So even sort of for PEPs, that's sort of tricky. On the other hand, this PEP formalism is something people do use in practice, partly successfully. So I think there's still sort of work to be done to prove why this is the case, why things work well. So the way they usually deal with them, I think numerically is, there's various heuristic ansatz. Something else you can do is you can try to do the same transfer operator business we did here, but now you do it for like the one-dimensional lines that sort of slice up your two-dimensional grid. So your transfer operator actually has many indices. So that seems of course problematic. So you can only do something like a narrow strip that's very wide and so on. But that's I think things that people do. I guess. So I don't know this so well, but there's this Holland framework, and I guess these, which is very similar to tensor networks in some sense, and people study these dichotomy theorems, sort of saying, which I think in this language basically means, can we prove interesting statements when we restrict our to certain subclasses? Right. I think. Yeah, that's right. Yeah.
So, it's natural in the
but
context of, and the gadgets that you allow in the Hollands are basically these linear transformations that you put over there in the correlation when you define the correlations. It seems to me like pretty much
that was my impression. I think people like some question that people ask there that maybe has only partially explored in this context is, what if you say, okay, let's not allow arbitrary tensors, but only certain ones. So for example, there are certain subclass of quantum states that we know how to reason about efficiently. For example, Gaussian states or what's called stabilizer states. So it's sort of a states that you can reason. It's like it's another sort of subset of this big Hilbert space, which is not somehow defined in this geometric fashion, but still can be represented efficiently. So one could ask, are there other classes, natural restrictions on these tensors, so that one gets something that's more tractable. Anyways, there was something I wanted to mention. So I guess the summary is that if you have some family of tensor network states, you get some, I don't know, maybe you could call it a computational model, I'm not sure. And you could relate this to sort of the ordinary, computational models. You could ask, how hard is it to do these contraction problems? In general, it's hard. Sometimes it's not so hard. It certainly does depend on the graph that you start with, on the allowed tensors. Maybe one brief comment that may be interesting. You could also ask about the quantum complexity of these objects.
To comment, I think that the Holland problem, this is the Valiant model of computation, is it's those things which are reducible to computing matching.
Yep. Yeah. Right.
If the graph is planar, then we know how to count them in polynomial time.
Yes.
So these are in that representation, I think the Holland problem, eventually, basically this correlation that you define. But if the graph is planar to begin with, then it's a polynomial time computation. That's a restriction on the graph.
But also on the the tensors then are locally.
The tensors is not. No, I don't think you need to.
Okay. Okay. All right. Yeah, maybe let me make one brief comment about sort of quantum complexity. So you could ask, here we're trying to reason about quantum states using classical complexity theory, right? Ideas from classical computation. You could also ask, so if you hand me a classical description of such a PEPs or a tensor network state, can I prepare a quantum state efficiently, right? So using a quantum computer. So that's something that's maybe a more natural question for some of us than for others. But you could ask this question, and basically what it amounts to. So suppose you had a, maybe I'll just put this somewhere here because it's sort of a side remark, and we'll come back to the rest. So suppose you had a machine. You give this machine a classical description of a say a PEPs or some other tensor network state. Classical description of tensor network state. Maybe even of a PEPs, just restricted to this two-dimensional family. And out comes a quantum state. That is this PEPs. Okay. So this is the quantum state. That is this tensor. Okay. And so you have this magic oracle, this magic black box that achieves this for this. So now you could look at a computational model, right, where you're allowed to do some classical pre-computation that, so you have some computation problem that you want to solve. So you get some problem instance, you get some input. Now, maybe you do some classical pre-computation. You somehow convert this into a tensor network description. So you do some classical pre-computation, maybe in, I don't know, BPP or something, or maybe just in P, because you can do the randomness maybe likely here. And now, well, here you get a quantum state, so it's natural to do something like BQPs, to do some, polynomial time-bound computation. And now at the end, you get yes or no. You could ask, how rich is this? What's the power of this model? And that turns out to be equivalent to what's called post-BQP. So that is, maybe that's only a sort of remark for the experts, but so that's basically the power of a quantum computer where you allow for post-selection. So what it means is you're allowed to do measurement, right? And then if you get measurement outcome 0, you're saying, okay, no, that's great. But if there's 1, you just try again, but it doesn't cost you time. Or in other words, you can always assume that your measurement gave you a certain result. And the intuitive reason is that, I guess there's something I didn't say before, sort of in quantum computing, that it's very similar, like a quantum circuit is very similar to a tensor network, right? It's also multilinear and all these gates, but the gates are unitary matrices. In these tensor networks, we didn't demand that the tensors were unitary or isometries or anything like this. And so this non-unitarity is what you have to pay for by doing post-selection. So you can emulate any linear algebraic operation or any linear map by a quantum computer if you're allowed to post-select. But in general, of course, the probabilities will be tiny that you get the right result. But here you don't pay for it. So I think this is the same as PP. I think sort of,
which is almost the same.
Which is crazy. Yeah, and so that's sort of in other words, it's also crazy, and we wouldn't. But that's sort of the thing. I think this is by Schuch and Sirac and friends. Okay, so I guess 10 minutes. So let me briefly actually talk about more about these one-dimensional systems. Maybe that's a nice way of wrapping things up. So I can erase 2 dimensions, and I can hide the quantum part. All right. And maybe this we don't need. So here we want to find tensor network descriptions, in particular ones matrix product state approximations. Let me briefly sketch the general scenario and then restrict to 1 dimensions. So this is about algorithms for finding tensor network state descriptions. I should say that I guess the whole talk was a bit more focused on approximating ground states, so something that has both a numerical flavor and then there's these rigorous results or these rigorous algorithms that start to be somewhat competitive. This whole formalism of tensor networks has also been quite a success in sort of related to kind of what one could call exactly solvable models, so sort of toy models of certain physical features such as topological order. So there are certain sort of it's like model systems that one wants to understand very well, and for example well, I guess it's something that's not topological order, but that was of interest was this AKLT Hamiltonian. But then sort of in topological order, there's this toric code and these stringnet models, and all of them have a very compact tensor network description. So that was one of the. I mean, maybe these are just words, but what I want to say is that apart from doing numerics and proving that numerics can work, there's also some theoretical insight that people have gained. But these problems have maybe more of a physics flavor, so I didn't want to emphasize them too much. But one can kind of like almost do sort of proof by pictures of some interesting physical properties in this way. So that is something that I'm sort of ignoring in this talk. I'm also ignoring things like symmetries, how to incorporate symmetries in this tensor network, even though I may have announced this in the abstract. Okay, so how do these tensors arise in nature? So suppose gamma is some graph, some interaction graph of a physical system, and for us it will always be some regular, lattice, like a line or square or something. But just for 2 minutes, say this is some graph. And you just have in mind a one-dimensional line. So that's not yet a tensor network or anything. That's a graph on which we want to define that's underlying our physical system. Now, how is this physical system then described? So this would correspond to a one-dimensional system, quantum system. Now, a quantum system would be described by a Hamiltonian, and usually we assume that this Hamiltonian is either local, meaning okay, what is a Hamiltonian? A Hamiltonian is a Hermitian operator on some underlying Hilbert space, maybe associated with this. Okay, I guess I'm jumping ahead. So here's a physical system. I think of each vertices on this interaction graph as the physical sites. At each site, I have a Hilbert space of dimension c little d. If I have n sites, then my Hilbert space would be CD tensor n. In general, it would be the number of vertices in this graph gamma. So now, what's a Hamiltonian? Hamiltonian is just a Hermitian operator in the space. It somewhat describes physics on the system. And a local Hamiltonian is a Hermitian operator that I can write as a sum of terms, each of which is again a Hermitian operator, but a Hermitian operator that only acts non-trivial on a few of the tensor factors. And actually, the meaning of the graph, of the edges in the graph, is that I only want the terms in the Hamiltonian to act non-trivial on sort of sites that are neighboring according to this graph. Okay, I could also look at edges that include more, these hyper edges that include more than 2, but that's sort of without loss of generality. So a local Hamiltonian is a Hermitian operator H. We are sort of summing over, say, all. Okay, now I'm sort of abusing this notation. Maybe let's say x, y are edges in this graph. I don't know, E gamma. And now there's some term h little xy, and this is some Hermitian operator that acts as the identity on all tensor factors except for the x and y tensor factors. Okay, so n is the number of sites in x that acts on non-trivial only on x and y tensor factors. So in this, it's like in this correlation function, right? I had sort of two operators. This was a tensor product acting on two sides. Think of something like this. So that's and we would usually normalize these terms, right? Because I will talk about things like a gap, so it's good to normalize. So maybe I'll say all of these terms have operator norm bounded by 1 or something like this. And I guess I said this, but yeah, so they're Hermitian. So this thing has eigenvalues on a finite system. And one thing of interest is the subspace corresponding to the smallest eigenvalue. Or let's just assume this is there's only one. And let's call this the ground state. Otherwise, it would be the space of ground states. So goal is we want to understand, we want to find, we want to approximate what's called the ground state. So T, sorry, I guess I didn't give this Hilbert space a name, this vector space a name, so it's CD tensor n. So this is the eigenvector, or n eigenvector, with eigenvalue lambda min of h. Okay. So that's what is by definition what is a ground state. We want to approximate this by what? By, for example, a tensor network state, and in particular by a matrix product state if gamma is just this line. Okay. So that's a bit like, right, you have some constraint satisfaction problem, you want to find a solution. But of course, in a classical constraint satisfaction, in the end, you have just some assignment of all these n variables. Here, this in general, this tensor is not a product of rank 1 tensors, but it's some entangled state. And we have some physical intuition about when is the state very entangled and when should it be well approximable by, for example, a matrix product state. And so one measure that has turned out to be useful is, again, a gap, a spectral gap. Now it's a gap of this operator H, not of some transfer operator. This doesn't exist anymore. Doesn't exist at this point, which is basically the difference between the lowest two eigenvalues. And so what is sort of the idea is, roughly speaking, because you only have these local interactions, most of the correlations or entanglement between sites, I mean, the entanglement should be local. So if I look at, say, in a two-dimensional system, if I look at some region A, we would believe that most of the correlations come from nearby sites. So the sort of on the one hand side, we would think of this meaning that the entropy should scale like the boundary of this area, not like the volume, and also that correlations will decay because they are sort of mediated by these local interactions. Okay, but of course that's things that these are statements that have to be proved. But that's sort of why one would believe that sort of having a gapped local Hamiltonian sort of on physical grounds implies, say, an area law and this exponential decay of correlations. Okay. And so this, in one dimension, such things have been proved. So I'll cite these results by Hastings, which I understand sort of rely on sort of a large body of work and techniques from mathematical physics, sort of that go back, for example, these Lieb-Robinson bounds that are something like a maximum speed of information transmission in these physical systems. So that seems like something that's useful to consider here. But that's kind of the things that go in. So in 1D, by which I mean this graph is just a chain like so. There's rigorous results. So first question is, right, does there exist a matrix state approximation? Second question is how to find it. So for the first question, we had two criteria. One was the area law, the other was exponential decay of correlations. And so both of them, so this is Hastings, have been established. One is sort of the exponential decay of correlations. In the ground state, sorry, yeah, these are all properties of the ground state, assuming this gap, and say assuming for now.
The gap is constant.
Yeah, it will enter the bound in a bad way in a second. That's right, yeah. So this psi here, this correlation length, will scale like the inverse gap, I think, roughly speaking. So what people call the correlation length. So I'm not sure if this. Well, yeah, it's roughly speaking like this, I think. And then he also proved an area law because at the time this was not yet good enough to establish that there exists matrix product state approximations. Area law, kind of saying that if you look at this this entropy of a subsystem, then I think it should be something like this, some exponential, and then I guess here there's this d is this physical bound dimension, this d, and then again there's an inverse gap. I think something like this is probably right. Yes, and so either of these two things, right, imply the existence of matrix product state approximations. And I guess one could say that things like this exponential decay of correlations, I understand, were established in relativistic systems in mathematical physics like decades ago. And I guess here that's sort of in a non-relativistic system with a Hamiltonian and so on. I guess similar in special cases, such things, area laws and so on, were established. But that's a very nice general result, basically relying only on these two assumptions. And so when people say having a gap, like usually what people have in mind is that you let the size of the system become large. That's your parameter. And as n becomes large, this gap should not close. It should stay constant or maybe go to 0 very slowly, say. So that's what one has in mind. So now the question is how to find it. So we have 1 minute to find the grounds. We have to find the ground state. So I think that there's kind of two answers. The one is sort of the non-rigorous answer. So there's an algorithm called DMRG, Density Matrix Renormalization Group, that people like to run in a numerics community. And I think what it does, roughly speaking, is it's like an alternating minimization scheme where you fix all tensors in your matrix product state except for one, and you're trying to minimize the energy, like keeping all fixed except for one. And that seems to work out very well in practice. But no one has yet proved that this should be the case. But by now, there are rigorous algorithms that are somewhat close in flavor, I would say. And so the best results, I think, are due to Arad, Landau, Vazirani, and Vidic. So maybe I'll just state what they would prove. So maybe I'll say how to find. So maybe I'll just say in practice this DRMRG algorithm, which is this alternating minimization scheme. But now we have also these rigorous results. So this is by Arad, Steflando, Umesh Vazirani, and Thomas Widig, saying roughly that you can find a 1 over poly n approximation. So this is sort of the distance, say a trace distance or Hilbert space vector distance, MPS approximation with in time something like 1 over the spectral gap squared, n to the number spectral gap squared. So this is poly time if the gap doesn't close. Okay. So I think that's basically what they have. Okay. So that's, I think, roughly speaking, the state of the art in this scenario. Now you could ask, are there any questions about what I'm saying here? So I guess I didn't explain how this goes about. I think sort of their latest algorithms, they're some local procedure. They have what they call an approximate ground state projection. So they sort of prepare sort of for small sort of subsystems. They prepare things that are close to the ground state of that system. And then they have 2 of these, and they try to merge them together in some hierarchical scheme. It looks not too dissimilar from these mirror networks, that I mentioned before. But anyways, so you're trying to merge them together, and then the dimension of your space so they're sort of maintaining a subspace of small dimension that is rich enough to capture the state. And so in this merging process, the dimensions multiply, so they have to truncate it again, and so they have to do some clever and careful analysis to establish this theorem, which is kind of making these existence statements effective in one dimension. So one could ask, what happens if this gap assumption is not satisfied? Say it goes to 0 when the system size becomes large.
Just about the gap. The gap is, let's say, a constant, but the norm of the mission operator is polynomial.
Yes.
Like n.
Yes.
So it's relative to the norm, it's like 1 over polynomial.
Right. That's right. That's correct. Yeah. Yep. Yep. Yes. Yeah. Suppose this gap is not constant though. Suppose it goes to 0. Then you sort of suppose this assumption that this is sort of larger than 0 and stays larger than 0 is violated. There could be sort of, roughly speaking, the 2 reasons. One could be that simply the ground state is degenerate. There's more than one vector with this exact eigenvalue lambda min, but there's still a gap to the next eigenvalue, right? So the spacing is gapped, but there's just a degeneracy. Another thing could be that you have some window of energies, lambda min, and lambda min plus some little delta, and inside here you have more than one eigenvalue, but only say a polynomial number of them, so a small number relative to the whole bit space. So I guess we call this the density of states in this regime is not so large. In this case, roughly speaking, this result generalizes.
I still don't understand something. I mean, you could just in terms of what's the meaning of n and what's the meaning of delta.
Yes.
It seems like I could add, like I could take this line of length n and add to it dummy, n squared. Since I increased n a lot, and delta as a function of n, didn't change. So delta is really the absolute.
I think yes, but everything here is on this line graph. Like it's
On the line graph. Okay.
yeah, it's all in this one-dimensional situation. Like as soon as you deviate, and even if you add like some branching thing at the end, a priori there's no result. Yeah, so it's all on the line graph. Now I'm trying to. I think there's. Trying to remember if there's some translation variance that is being imposed.
I don't think there's any translation.
I think not. Yeah, but okay, but don't. Yeah. Yeah. So okay. So I think that's basically it. The only comment I want to make. So I think that's the right normalization, but maybe we should check. If you could consider the situation though where this gamma goes down faster than I guess in this normalization. No, I think No, I think it's good to normalize like this, right? Because you want this energy to scale like the system, like the number of sites, roughly speaking. So I think it's good to normalize things like this. So then you have this gap. If it goes to 0, if the gap closes, well, if sort of the number of states in some constant energy window it may be larger than 1, but if it's not too large as the number of sites in your chain increases, then that's still okay. If the ground state is degenerate, that's also still okay. I guess one is, you could think of a special case of the other. So that's sort of also done by those guys. There's some results if in more dramatic situations, but maybe that's more. I mean, that's more using terms from the physics community. There's something known as conformal field theories, which describe systems where this gap assumption is not at all true. There are some rigorous constructions of matrix product states by Koenig and Scholz. Also constructing matrix product state approximations. And we have done some work on a different kind of network, not this one-dimensional chain matrix product state network that we drew here, but a network that has this hierarchical self-similar structure, proving that for certain simple systems where also the gap is 0, one gets good approximations. So these are sort of works where in some sense one studies explicitly given systems, which one in some sense can solve by hand-ish, but it's still highly non-trivial to find these tensor network approximations. So usually you could think of it a bit out like, some of these systems you can solve by a Fourier transform, but a Fourier transform is very non-local in space. So you're trying to solve, in some sense, a simple problem but you want to bring it into a certain answer. So there are some results along these lines. So the Koenig-Scholz result I mentioned, some work I've been doing with some collaborators, including Brian, who's spending some time here. Which I guess is the first rigorous result for something that is not a matrix product state, but this other kind of family of tensor networks. Yeah, maybe that's all I had to say. Thanks.